right, next up, we're going to look at an example where we're given a triple integral in Cartesian coordinates and we have to convert it. So here's the integral, -1 to 1, negative root 1 minus x squared, positive root 1 minus x squared, and integral from x squared plus y squared to root 2 minus x squared minus y squared. The function inside was z, and we're integrating dz was this integral, dy was the middle integral, and dx was the outer integral. And if we sit down and try to evaluate this, it's a huge mess. If we evaluate it in spherical or cylindrical coordinates, it'll be a little bit easier. And so our first step here is going to be to try and figure out what we're looking at. And so let's see, here's my z, my x, and my y. I'll fill that in a second. And then here's my x, y. So my x goes from -1 to 1. So that's something. And then if I look at my bounds for y, hopefully at this point we're getting really good at seeing that if y equals plus or minus root 1 minus x squared, that came from y squared equals 1 minus x squared. That came from x squared plus y squared equals 1, circle, radius 1. It would have happened a lot in polar coordinates. So looking at just these two outer integrals, this tells me sort of the region that I'll denote by star is a circle in the xy plane with radius 1. So here's my root 1 minus x squared. Here's my negative root 1 minus x squared. I start down here, go up here, and my x has limits from -1 to 1. Oh, I'll do it like this. That's kind of a way that we represented interval limits versus curve limits before. Okay, so I understand what these two are telling me. And then the second one is a little bit harder for me. So my lower bound is z equals x squared plus y squared. And my upper bound is z equal root 2 minus x squared minus y squared. And maybe we wouldn't have looked at this type of thing so much in the past, but if we use the exact same processes with y, we see that this means z squared equals 2 minus x squared minus y squared. So this is x squared plus y squared plus z squared equals 2. This is a sphere with radius square root 2. So somehow that upper bound in z is a big sphere shape, which we've established previously I cannot draw. But you're just going to have to accept with me that that's a sphere right there. And then this other shape, z equal x squared plus y squared, you might not remember, but it's one of those ones that's kind of bowl shape. So when x and y get bigger, z goes up. So I know that as x and y get bigger, z goes up. If I just looked at like z equals x squared and z equals y squared, that's what that would look like. So it's one of these. Let me draw that in a way that, oh, I know. We'll put our sphere equation back later, but I need to be able to draw there. So it's one of these, like that. So maybe you would have guessed the sphere, but not this one. Wouldn't remember that from the library of functions we learned like in the first section of class. So my hint would be think about z equals x squared, y is 0, z equals y 0 plus x squared. Sorry, y squared. Just like take each variable to 0 and then sketch that curve and then connect them. And that's how you could remember that that's a bowl shape. A lot of you have used this shape in your projects too. I'll leave that hint there, I guess. Okay, so this is my x squared plus y squared bowl, and this is my root 2 minus x squared minus y squared sphere. And the sphere is my upper bound, and the bowl is my lower bound. So everywhere in Z, I'm starting on the bowl and going up to the sphere. This is kind of like you took a bowl and slapped some kind of circle object in it. And it happens that they intersect right here in the circle, which happens to be that star projection down into the XY plane. Because if you think about this in the direction we usually do it, you would have found these two bounds, set them equal to get this part. And so when they're equal is when they intersect. And when you project it down into the XY plane, it's this circle. So that's the region we're thinking about. And how are we doing on time? Okay, if we had a lot of time, I would start off by saying, okay, there's a sphere. So I guess I should use spherical coordinates to show you that that's not the way to do this. But we don't have time for that, so I'm just going to say, no, sphere is misleading here. If we try to set this up in spherical coordinates, the sphere is great, but this bowl shape isn't built in spherical coordinates. It's got an x squared plus y squared, but not a plus c squared. And so this thing is hard to describe using spherical coordinates. Instead, this is the type of shape that works with cylindrical coordinates because it's made out of circles, but z isn't in a circle shape. You know, it's flat on top. So cylindrical is going to be easier here. And the reason is because we have circles, not spheres, in some part of our region. And so now we just have to think about how to set up our cylindrical coordinates. So I'm going to go ahead and guess that we're going to do dz dr d theta. Maybe we have to change that once we start writing stuff down. We'll see what happens. And I didn't forget about my r right there. And then my function inside before was z. But since z is a part of cylindrical coordinates, I don't have to convert it all. I can just write z and leave it as it is. And on that same note, because z is a part of cylindrical coordinates, I can keep it same bounds as before. But I'm not going to write them right there yet because I have to remember that I have to convert to polar coordinates. So everywhere I see an x squared plus y squared, that becomes an r squared because x and y are gone. So x squared plus y squared becomes r squared, and root 2 minus x squared minus y squared is the same as 2 minus r squared. All right, I got that. And now I just have to think about my r and theta bounds. So when I'm creating my theta bounds, I think about the shadow my shape cast down into the xy plane. So I look over here, and I start at the positive x-axis, and I spin all the way around. I'll go ahead and draw that picture right here too. So, oh gosh, going all the way back to the start of all this where we introduced cylindrical coordinates, we said z takes on its own value, and then x and y are defined by r and theta like they normally would. So that's why we're looking at this projection in the xy plane. And so when I look at this, I know that my theta starts here, theta equals 0, goes all the way around, theta equals 2 pi. And that also helps me see my radius starts at 0, the origin is covered, and goes out to 1. And that's it. I can go ahead and put them in here. And we're good. There might be a temptation to say, okay, well, that's the radius at the biggest point, but like, here, my radius is smaller. Here's a smaller circle that I'm thinking about. And that's true, but that's covered by taking my radius equal to 0. Like, here's a radius 0, here's a radius 0, and then it can get as big as you want, up to 1. Bigger, 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 1, and then get smaller again. So it's bound between 0 and 1. That's why I only think about the biggest radius when I'm actually, when I'm actually writing these bounds. But if you're concerned about the fact that there are smaller radii, that's okay. They're covered by the radius falls between 0 and 1.